Alright, so let's look at the second question. The cost of using it for 24 hours at 30 kobo per kilowatt hour. So first of all, we'll calculate the power consumed. And that's IV. And what's the power consumed? IV, that is 0.7 times 220. 0.7 times 220, that's power consumed in the primary coil or the mains. Power consumed, we have 220, and it's in watts, so we convert it to kilowatts. So our main focus is on the primary, to know the power consumed from the primary coil, not on the secondary coil. So power consumed in the primary coil is 0.7 times 220, that's over 1000 to convert it to kilowatts. Then we'll multiply by 24 kilowatt hour. Oh, sorry, yes, by 24 kilowatt hour. Total power consumed in 24 hours. So by 24, then we multiply it by 30 kobo. So the formula is just simple. The current in the primary and the voltage in the primary, we divide it by 1000, okay, to convert it to kilowatts. Then we multiply by 24 kilowatt hour and multiply it by 30 kobo, which is 0.3 naira. So we have 1.1 naira. It's the same formula for calculating the cost of electricity for your normal Ohm's law. V equals to IR for under electrical energy and power. Now before we round up, let's just look at power transmission, and we'll end with that. Power transmission. So we have that power generated at power stations are distributed over large distances to consumers through metal cables. I told you before, high tension cables, metal cables. Power is given by P equals to IV and can thus be transmitted either at low current and high voltage or at high current and low voltage. So there are two ways power can be transmitted, either at low current and high voltage or at high current and low voltage. Now, because the metal cables through which the power is transmitted have a certain amount of electrical resistance, every metal cable, every wire, copper wire, tin wire, any wire I can mention of, they have a certain amount of resistance. Transmitting power at high current is very, very risky, because when you do that, you're having issues with the tension with the cables every time. When you do that, it will lead to loss of energy in the form I square R. That means it will lead to power loss. As most times when you see calculations under resistance, voltage, and current, you see where they say calculate the power loss in the wire. That means what you have there is high current. High current has been transmitted. High current has been transmitted. Okay. Now, to avoid this, power is therefore transmitted at high voltage and low current. Power is therefore transmitted. So that's the best form to transmit power, at high voltage and low current. This is known as what? High tension transmission. So that's where we got the word high tension from. So high tension transmission simply means transmitting power at high voltage and low current and high voltage. Low current leads to low energy loss. It's not as if there will not be energy loss, but it will be low compared to when you are transmitting at high current and low voltage. So low current leads to low energy loss in form of I square R also. And also, since the lower currents require thinner cables, don't forget, I is equal to V over R. And V is equal to IR from Ohm's law. So, since the lower currents will require thinner cables, cost of cable materials is considerably reduced. Because if you are transmitting at low current, you don't need thick cables. You can also use thin cables. Current can flow easily because you are transmitting at high current and low voltage. So one of the advantages is that energy loss is reduced. And number two, cost of cable materials is also reduced. And also, step-down transformers are used to reduce high transmitted voltages. So number three, we can use step-down transformers, and that is most of the transformers we have around. They are step-down transformers, because most times when we have those high tension transmissions from those power stations, most of the times you see full voltage, not full current. Many people call it full current. I think like low current and full current, they are called full voltages or low voltages. So most times you see full voltages. So that is why you see most of the transformers we have are step down transformers, to step down the current, to step down the voltage, to step down the voltage. So step down transformers are used to reduce the high transmitted voltages to lower voltages required at homes and factories. Required at homes. What your house required is the step down. You cannot use, if the voltage transmitted from those power stations to the transformers are transmitted to your houses. You see many times we have electrical faults, devices are burnt and all that. That we have experienced it most of the times. The reason is because most of the times in our houses also we don't have step down, step down, step down, step down, or the amount of voltage the transformer can step down, or what we have is step up transformer, or the amount of voltage the transformer can step down is little, or most of the times the transformers we have are step up, not step down. If it's step down transformers we have, they will step down those voltages. That's why most times after some time you will see that the voltage will now go low a bit. Yes, so that's the work of a step down transformers. So they are used to reduce the high transmitted voltages to lower voltages required at homes and factories, because those gadgets you have in your homes, they also have power rating. So when the voltage transmitted from the transformer is more than the power rating, it will burn off those gadgets, it will burn off those devices. So quickly before we round up, let's look at this advantage of AC over DC in power transmission. So AC is preferred to DC in high tension transmission because the AC can easily be transformed to high voltages with very low energy loss. Like I said in the beginning, it is sinusoidal. It changes high, low, high, low, high, low, low, high. So the voltages can be stepped up or down by transformers, while DC voltages cannot. Direct current voltages, they are one-way drive, they cannot be stepped up or stepped down. A transformer cannot, of course, be operated with a DC, because as soon as the current has attained a steady value in the primary coil, there is no change in the magnetic flux. And once there is no change in magnetic flux, Jesus, the energy loss will be much. It will be very, very much. Very much. And because as soon as the current has attained a steady value in the primary coil, there is no change in the magnetic flux in the core. There ought to be changes, regulations, alternations. But since there is no alternations in the core, no EMF will be induced, because it is the alternation and the variations in the magnetic flux that brings about EMF being inducted in the secondary coil. So no EMF will be inducted in the secondary coil. Now DC would require the use of motors and dynamos in order to produce a voltage change. So for voltage to be induced, we now need to add an extra load to the DC supply called in form of motors or dynamos to convert some mechanical energy into electrical energy in order to produce a voltage change. This will bring about greater power losses. I said it earlier, greater heat losses, greater power losses than when AC is used. So therefore, a transformer can be modified to step up a DC voltage by connecting a make and break device at the primary circuit. What does that mean? Make and break. We're talking of something like a fuse. So that when the voltage is high, instead of it affecting gadgets in your house, the fuse will be burnt. So when the fuse is burnt, we call it circuit breaker. When the fuse is burnt, it will be burnt in place of your gadgets at home, in place of your devices at home. So a transformer can be modified to step up a DC voltage by connecting a make and break device at the primary circuit. So we stop there. You can read up induction coils. Maybe in our next class we'll talk more on induction coils and the way it works. Thank you very much.